All right, let's get started. Any questions on the homework? Do we need to go through it, or do you feel pretty good?
Pretty straightforward. A lot easier than sign.
It's easier. Why is it easier than sign?
Well, yeah. I mean, it's because you already saw it.
Oh, because you'd seen it already.
Yeah.
It's essentially the same process, right? I mean, it's instead of subtracting, you add, and then that's basically it. But those are pretty important ones when we look at circuits and systems, because what we'll find with a lot of real-world systems is they tend to ring. So even though you energize a system with a DC input, which is called a step input, you'll actually see some ringing on the output. If anybody here been involved with the process control industry, paper mills at all? We talked a little bit about doing bump tests. Well, one of the things you look at is you see how the system responds. And for what's called good quality tuning of your system and good setup, you actually want what's called quarter amplitude damping. So each successive cycle, you have 1/4 the amplitude that the previous cycle had. And that's sort of the ideal operation and tuning of a system. You do a bump test first, and then you see how your system responds. And when it's kind of ideal is this cycle is 1/4 the previous cycle in its amplitude. No, you're not changing the frequency at all. Normally what you do is you just change, well, it depends on what it is, but normally you just change your proportional constant.
I guess could you go in?
Well, it's not going to make a lot of sense until we get through some Laplace, because to see how to go from DC to that, it'll make more sense. So if you want to see me after class and we can talk about it for tuning.
I remember hearing you talk about it.
Yeah, it's quarter amp, and it's all based on control systems and whatnot. So, all right. So let's look at our first sort of key Laplace and why we can use Laplace. Let us take the Laplace transform of f prime of t. How's that? Because anything we do in the time domain, we should be able to do the equivalent of that in the Laplace domain and get respectable or decent results. So we do exactly what we did before, 0 to infinity. And I'm going to put df of t dt e to the minus st dt. How do we get rid of that? How do we make this work? How do we actually come up with the integral? Well, this one is a really tough one, and we can't combine e to the st's because we don't know what the function is. So we are going to integrate by parts. Do you remember u dv equals uv minus v du? Right? Probably, well, if you did 127, you would have seen it there. If you're in calculus, if you're in differential equations, I don't know if they do a lot of integration by parts. Okay. What's that? Oh, really? You do a lot of it in that calculus class? Okay. Differential equations?
What page are you on?
I'm on page 9. So, here's the thing. The general rule of thumb, I think, to do this is to pick something that is relatively easy to integrate and let the u be the rest of it, is sort of the rule of thumb. I don't know if your math professors have mentioned that, but it's not always easy to figure out what u and dv is, but usually you pick the easiest one to integrate and then let u be the other term because it's easier to differentiate than integrate, and then you're all set. So what we're going to do is we're going to let u equal e to the minus st. du is equal to minus s e to the minus st. So I know that in my function I want u to be equal to this guy, right? And then my du is just going to be the derivative of that with respect to time. And I'm dropping off the time here, but we're dealing with variables in time, so we'll go from there. My v is going to be equal to f of t, mainly because my dv is going to be equal to the derivative of ft, right? And since these canceled out, that's kind of how you ended up with those terms. So I picked my dv to be the easiest one to integrate, right? It's pretty easy to integrate the derivative of f of t. So I could integrate it immediately to get my f of t. And then my u was the rest. So I basically picked these two and then calculated those other two, all right? I'm just lining them up that way because I'm trying to do derivatives and the straight functions as they are. So let's go ahead now and do our Laplace of df of t dt. Now we're going to start to integrate in that equation, but we're going to break it up. So I have e to the minus st f of t evaluated from 0 to infinity. That's my uv, right? So if you remember integration by parts, I've got my uv here, but I still have to evaluate it at its integration limits. Otherwise, I'm still left with the variable t, right? So my integral should not be a variable. I shouldn't have the variable that I'm integrating with respect to in there. And then I subtract from that 0 to infinity minus f of t s e to the minus st dt. Okay? Questions on how I got that? Cam?
So that equation you just wrote out, is that the uv minus integral dv?
This is uv, and that's the integral of v du.
So do you need to integrate the e to the st ft? Or is that just...
Do I need to integrate this?
No, the first one.
No, it's already been integrated, right? But I'm evaluating it at the integration limits. Okay? Any other questions here? All right, so I'm going to evaluate here. E to the minus st when it's at infinity is what? 0. So 0 times f of t is 0, isn't it? Now I'm going to subtract the lower integration limits. So 0, this is 1. E to the minus 0 is 1 times f of t. But it's not f of t, it's f of 0 because I'm substituting in my value of time for my lower integration limit being equal to 0. Now, I'm going to subtract, or plus, everybody see what's going on there?
Yeah, you just plug it in 0, right?
I did the upper integration limit, which is infinity.
Yep.
E to the minus infinity is 0. So I don't care what my function is, it goes to 0. My lower integration limit, it's e to the minus 0, which is 1. But t is equal to 0. So that means f of t, I have to evaluate that at t equals 0. Right?
Because infinity, it just goes away. So
Yeah, because it's e to the minus 0. E to the minus infinity, which is 0.
wouldn't it be e to the minus 0,
E to the minus 0 is what?
1?
Right.
You put 0.
No, I didn't.
Oh.
I have a 1 here, right?
Implied one.
Pardon?
It's an implied one. The F is this one.
If it, I'm sorry.
It's an implied one.
Oh, an implied one. I didn't hear you. I'm sorry. Yes? No?
Yeah.
Okay. What is this? Should be awfully familiar. That's the definition of Laplace. So this, the Laplace of the derivative of a function is equal to s, f of s, minus f0. Do you remember our motivation when we started this material, chapter 5? Using algebra instead of calculus. Very good, Alex. Didn't we just get rid of a derivative in the time domain? Isn't that equivalent to multiplying by s in the Laplace domain? I don't have to do any derivative there. All I need to do is take whatever my function is in the time domain, f of t. I bring that to the Laplace domain, make that f of s, and I multiply by s. Then I subtract whatever initial condition is. This is going to be a number, right? That's the initial charge on the capacitor or the current through the inductor. So we would subtract that away. That is a really, really important one, and very important that you understand what's happening. Because if you can't get and understand S, f of s. You don't have to understand the actual math behind it, because I don't expect everybody to be a whiz at integration by parts. That's okay. Fair enough. But what's more important is that you have to understand that taking a derivative in the time domain is exactly the same as multiplying the Laplace transformed equation by s. And then we don't have to do we don't have to do calculus. We just do algebra. Very, very, very important. Otherwise, if the derivative in the time was the same as the derivative in the Laplace, forget it. Why bother? It's the same amount of work. But now it's just multiplying. You want to do the integral?
Nothing I would love more, Paul.
All right. Would you like to come up here and do it, Lincoln?
No, not even a little bit.
I thought you said nothing you'd love to do more. So change it tune.
Then do it, not necessarily do it.
To witness it being done.
Right.
I see. Got you. Okay. So this is a double integral. Okay? So same approach. What's the easier of those two to integrate? Well, clearly I'm not going to put the integral of f of t in there, right? Because that would be a real pain in the keister. So I'm going to make dv equal to e to the minus st, which is going to allow me to calculate v. E to the minus st over s, my negative here. So now I have my u, which is equal to the integral of f of t. So my du is equal to f of t, right? Same integration by parts. And this may be a good thing or a bad thing, but this is the only time in this class and the follow-on class that you'll have to do integration by parts, is proving these. All right. Pardon? Well, pretty much, once you get past the introduction to Laplace and knowing how to do these derivations, we don't do a lot of calculus in this class. That's the whole reason, right, of doing Laplace in the first place. Why do Laplace? Well, because we don't want to do calculus. So wouldn't it be kind of a not very nice guy if I said, oh yeah, let's do Laplace, and then
Weed people out.
weed people out? No. We will have to do a lot of calculus, though, when we get to Fourier. There's no other way around it, but that's really more of a topic. We used to not cover it, but I like to cover it a little bit because it helps you understand the harmonics, the concept of harmonics. And it's really important in industry because, as I talked about this weekend, I set the second harmonic and the fifth harmonic restraint on a transformer differential element. Would you all know what that is?
Oh, yeah.
You would? Well, the only reason why is because as engineers, it used to be, I know what a harmonic is, but that's it. I don't care. Now, you're actually using it to block the operation. That's what restrain means. It's preventing operation. So if I ask you to set the second and fifth restraint elements, percent restraint, you kind of need to know what those are, right? I guess. But it's a lot of math. So, but we don't have to worry about that now. We'll worry about that at the end of the semester. So now my Laplace of my integral of f of t is equal to the integral of f of t dt e to the minus st, right? That's uv. Right? Minus the integral 0 to infinity negative e to the minus st over s f of t dt.
Paul, I'm sorry.
Question?
On UV, what happened to the negative E, the negative ST over S? Where did that go?
The negative, say that again?
So UV, where you said is the integral of f of t dt times e to the negative st. What happened to negative e to the negative st over s? which you had as V.
I think you switched V and DV.
I switched V and DV. Hold on.
It's supposed to be UV.
It's, yeah, the integration by parts needs to be, and I have it in the notes. Where am I? It's UV minus VDU.
Right.
Right.
So this is V.
Is negative e to the negative st over s, but down bottom you just have the integral of f.
Oh, okay. Yes, so let's put the negative over here
Okay.
and like that. It's still going to work out, should work out the same.
Was just making sure.
No, you're right. It needs to be in there. I missed that part. Yep, thank you. So now let's go ahead and evaluate. So at infinity, e to the minus infinity is 0. Right? So my initial value is 0 minus e to the 0, right?
It's 1.
E to the 0 is 1. 1 over s. So this function here is f of 0 divided by s.
So does that just get rid of that integral?
Yep.
So you can ignore the integral?
Well, that's the integral from 0 to infinity.
Right, it's the integral of 0 to infinity. So it's the integral. These two are evaluated at the same value, right? Both of these have to be evaluated 0 to infinity. So at 0, it's f of 0. Okay?
So the next one will be f of infinity.
Pardon?
So the next, when you do it as, when you evaluate it from infinity, it's going to be f of infinity.
No, infinity.
It's e to the 0. I mean, e to the infinity is 0. So this is f of infinity times 0 is still 0. No matter what, it works out to be 0. So then this becomes f of t, e to the minus st, dt is integral from 0 to infinity. Isn't this just going to be equal to f of s divided by s plus it's the same approach, but different result. Derivatives are multiplying by s in the Laplace domain. Integrals are dividing by s. And that's it. What other differential equation thing would you have to do? So we don't have to do any differential equations. These two are essential. You should write this down in your notes. F prime of t is equivalent to s f of s. And what we'll start to learn is we're going to get rid of initial conditions to simplify our world. But f prime of t is take s, multiply by f of s. Integral of f of t is take f of s and divide by s. What about third, fourth, fifth, sixth, seventh, eighth, ninth, whatever derivatives? Just keep multiplying it by s. Same thing with the integrals. Just keep dividing by s.
So the second derivative is s squared, f of x, and third s cubed.
Yep. And then you would just be subtracting initial conditions. In some cases, you're going to have s prime and s times f prime of s. You know, that initial condition. But we almost always throw those out anyway.
Can you, so the second derivative of
The second derivative, you're basically going to multiply s squared,
s squared, and then the third derivative would be s.
s cubed. Yep. Same thing with integration, but you divide by that same order.
And then f of s, you're not doing f of s squared. S.
No, f of s is stayed, and that's a good thing, because this is our time domain transformed function. If we had to square f of t and do it, whoa, that's a lot more work, and there's no advantage to it. So all we're doing, again, integration and derivatives become multiplication and division. There's no calculus. Very powerful. I will pause to genuflect, right? This is a big deal. This is the whole reason why Laplace is the key. You don't get this, you don't see the power of Laplace. Questions? Nobody's impressed. That's okay. You don't have to be impressed. Well, you know why you should be speechless is because that whole differential equations class, you're going to be able to forget it. You really, that's the thing. Engineers, mechanical, electrical engineers, we do almost everything in the Laplace.
I was just told that by an engineer, just in an interview, when I asked for the class, don't worry about it.
Well, it depends on the industry, but you might actually see the S variable a lot. Like control systems, you see a bunch of S variable stuff all the time. That's because we don't look at derivatives, we look at the S. If you do a lot of system modeling, like if you were to go to a plant and figure out, the tank does this and the valve does this and the pump does this, that you'd have to actually write with differential equations, but most engineers don't get into that level of detail. So,
We should work to get that dropped there and just count this as a differential equation class.
we can't. Maybe we could.
Yeah.
I did have a conversation with somebody out at a national conference, and he was an electrical engineering technology faculty as well. And I was telling him what I was covering in the power systems class, and he's looking at me. He's like, "How do you cover that? Per unit? Oh, that's no big deal." But I told him we did load flow and short circuit and symmetrical components. He's like, "How do you cover all that?" And I went on to explain to him that our students take differential equations as a requirement. He was shocked. He's like, "No way. Your program actually requires students to take differential equations?" I said, "Yes, because that's what our industry wants them to be able to do. They want them to be able to do Laplace." So.
I don't know about well, I know most of these guys are in my differential equations class, but I think I've learned more sitting here. About differential equations easily.
Well, just be careful. That's not a fair comparison, and I'll tell you why. Because I'm doing things very specific to electrical, which you already understand. So the differential equations that we've presented here are stuff circuit analysis. You know that. So how do we solve circuit analysis? It's all relevant. Where that person has to do things for mechanical, for civil, for chemical. I mean, they make things not necessarily relevant to your major because they want to be inclusive to everybody.
We just did a problem about Jordan and Peter having romance.
Nothing wrong with that?
Yeah, see, I took the difference with Jordan during this time. And the kid that would have understood it in your class more than they did in the Roman equations class.
Oh, good. Maybe I should teach math.
Seems more like they're just conditioning us to wake up early. I think every differential equation
This isn't crack it on.
is at 8 a.m. 4 days a week, so.
Well, that's okay.
No, that's fine.
It's good to get up.
Yeah, I agree with that.
Well, let's talk about Laplace. Now we see the motivation for Laplace, and we see why it is this way. Our next step is we can do this. If we can do all our work in Laplace and go back to the time domain, it would be great. Except for this one little gotcha. That little gotcha means it's not as easy as it appears. Yeah, f1 of t times f2 of t does not equal f1 of s times f2 of s. So when we have stuff that's multiplying in the Laplace domain, we can't just bring it back to the time domain because they're not equivalent. What we can do, though, and what we will do, is do that. We will add the two functions in the Laplace domain and then individually bring those back to the time domain, and that's okay. No, we don't need to. We're not going to multiply them together at all. We're just going to separate them, so go from f1 times f2 and come up with two new functions in the Laplace domain. And then once they're separated, then we can do this. We'll do them individually. So we'll go to the Laplace domain, do our work, and then when we're ready to go back to the time domain, we'll separate the two multiplying functions into two additive functions, take those back to the time domain individually, doing inverse Laplace transforms, and then we get the exact same results. The output will look the same. The function wouldn't be the same as if we multiplied them, but in terms of the output, it's perfectly fine. So this is what we're going to be doing. And how do we do it? It's called partial fraction expansion. Almost everybody here has seen partial fraction expansion, I'm assuming, right? Is that 122? No, that's pre-calc, isn't it?
Oh, I don't know the numbers.
I think it was Calc 2.
Calc 2 is when you do partial fraction expansion?
Yeah. With all the negative.
Calc 2 was, it wasn't supposed to end at Calc 2, you got it as partial fraction.
I'm surprised because that's just all it is algebra. Has nothing to do with calculus. That's the only thing you get out of it?
Simplify the integral part of the expression to make an easy integral.
Okay, so sort of the same thing here. But usually I thought you were taught it in an algebra class because all it is algebra. So the whole thing, and I'm setting you up a little bit for next semester. Our Laplace domain function, f of s, has a numerator that's a function of s, and a denominator that's a function of s. And it's, s to the 7th plus 6s to the 6th plus 22s to the 5th, etc., divided by 9s to the 8th plus da-da-da-da-da, right? All those s's are multiplied out. What we want to do is take that down into on and on and on. How many alphas do you need? Do you know?
Number function.
Nope.
Oh, double.
Numerator of s over the denominator of s. That's what n and d stand for. Michael?
Paul, in your typo, you have A and A, but then you have A and B. So it should be like A, B, C, or it should be A all across.
Let me look.
I thought it was A all across, but you just changed your alpha.
No, it should A, B, etc., because you're going to have different constants. Okay, so that's A plus B plus C plus D. Yes, sir?
And A and B are your constants.
Those are constants that we have to solve for.
Right.
This number of A, the number of constants we have, or the number of fractions, is going to be equal to, try to figure out a way to write this clever, so, can't write it that way, B of S you're going to have m. M is the order of the denominator. In this class, the order of the denominator is when you multiply everything out, you have an s to the 7th, s to the 8th, whatever the highest value s term is the number of terms that you'll have there. Okay? No? Gil, you're the one raising your hand?
Well, I guess, yeah, no, I understand why it's got to be the same number of, well, the n got to be, because if we have a polynomial, to make a polynomial with fraction, we got to...
Exactly.
Yeah,
Does everybody understand what Gil just said? You have an s to the m is your value of your polynomial, right? So let's do one out. Right, but we're going to use n and m, yeah, because I want to be confused. So we can see this is s squared plus 3s plus 2. Right? So then we have s cubed plus, let's see, I have 9 and 11s. How many roots? So these are the roots of this equation, right? If I put in -1 into this equation, what's the end result? 0. A root is when it evaluates to 0, right? So this is going to evaluate to 0. If I plug in -2, 0. -3, 0, because these two are the same, right? So if I plug in -1 in here, -1 plus 1 is 0 times a number is still 0. So these are the roots of this equation. And the number of roots that you need is equal to the highest order s term, or the order of the polynomial. And it's almost always going to be in the denominator. We only really care about the denominator, not the numerator. All right? So, let's do partial fraction expansion. And I'll do it a slightly different way. I want you to give me f of t. So, the way that we do this is we have to solve for the roots of this form, but only of the denominator. How do you solve for the roots of this?
You put it in negatives.
You factor the denominator.
No.
How about we do the quadratic equation? It's a second order system, right? So we just do quadratic equation and then we can get there from here? No? Can you unfoil? You might be able to by looking at it, but I just tell you to use a quadratic equation because if it's not obvious to you, quadratic equation always works. Right? Quadratic equation is negative b plus or minus the square root of b squared minus 4ac all over 2a. You also might have seen it in pre-calc too, right? Sometimes I bring that back up again.
We did that in college algebra.
College algebra, isn't that pre-calc? No?
It was college algebra, then it went pre-calc.
Oh, okay.
It's different between Eastern Maine and New Maine. Because I took pre-calc here when I first went here. Then I went back to Eastern Maine and it's like college algebra. I don't think they do the.
It's like algebra 2.
Okay.
They don't do like a college pre-calc.
But they don't remind you or refresh you of this in pre-calc?
I'm sure they do.
You took pre-calc in high school? Oh.
So that was a while ago. That's the last time I saw this was in high school.
Okay. Well, now you have it. Learn it because you will use it a lot. So negative b plus or minus the square root of b squared minus 4ac all over 2a. Remember that.
What?
That's equal to, what's the square root of 1? 1. So negative 5 plus or minus 1 divided by 2 is negative 2 and negative 3, right?
Yeah, negative 2, negative 3.
So f of s is equal to 3s plus 7 over s plus 2 times s plus 3. Another very important thing when we do partial fraction expansion, your roots are what this equation evaluates to 0. So if I have a negative 2 here, what do I need to make the factored forms out? What do I need to put in to one of these so that they make it to 0? You put in the positive of this. So anytime you go here and here, don't forget to take the negative of those numbers because these are the roots. I can't plug in a negative 2 here and have a negative 2 here and evaluate that to 0. All right? That's another very significant, important element there.
I thought that it was always the highest one though. So wouldn't it be
Always the highest one?
always the high, like S plus 3. So wouldn't
I'm not following you. I'm
I
sorry.
guess I got confused along the way.
Which part?
Earlier, I know what you're doing here, but earlier you said,
I said the number of roots that I need is equal to the highest order of the polynomial.
yeah,
So what's the order of the polynomial?
squared.
2.
Yep. So minus
How many roots do I need?
2. Okay.
So now you separate.
I got you. I guess I was looking at your example and I saw s plus 3 and I was thinking s squared or s to the third. So, and I was thinking it was always the biggest number was that.
Nope. No, it just works out that way.
So it's just 2 roots now. And then
Yes.
it would be 4 roots.
Yep.
And then another thing probably everyone else realizes it, but AC, which one's your A and which one's your C?
Which one's my A and which one's my C? Oh, this is A, B, C. All right, so partial fraction expansion says This is equal to capital A over S plus 2 plus B over S plus 3. I'm going to show you a different way. If you don't like this way, you don't need to do it. But I'll tell you why I like this way, because when we start to deal with things with sines and cosines, you'd actually end up with complex numbers to combine them together. There's another way to work around that that makes it a little bit more straightforward when you do this. So I have this. What I'd like to do is I'm just going to multiply both sides by whatever's under A. So let's take 3s plus 7 over s plus 2 times s plus 3. And now we're going to multiply both sides by s plus 2. Okay? Just multiplied both sides by s plus 2. Do you agree with that? Not a lot of yeses.
Why B when you do it at s plus 2 and not s plus 3 there? Because you're just trying for A.
Say that again?
You're just trying to solve for A.
I'm not doing anything yet.
Well, isn't this one of those things from Calc 2, and then you plug it in for B?
Yeah.
And
It could be. It depends on who you had for Calc, too. Some people do it this way. Some people just equate terms.
Yeah, because Paul showed us the.
Yeah, okay, so then I can skip this? We can go right to...
No. Either or. Some of us didn't have this.
Okay. I was kidding. I wasn't going to actually skip it. So we multiply both sides by s plus 2. Yes, sir?
Back to that question, so why is it s plus, so you're multiplying.
I'm just picking whatever's below A. And I'll tell you why in a second.
Going with that.
Yep. So now let's cancel out some stuff. And rewrite what we have. Right? Now I would like to solve for either A or B. I don't care. I need to solve for both of them. Is there a way that I can solve for A or B with the recognition that this is a linear equation? And the definition of a linear equation means if I solve for A or B at any value of S, that A or B is valid for that entire equation. So if I solve for A or B at S equals 1, A or B at S equals 2, they should be the exact same A or B. That's the definition of a linear system, right? Your constants don't change. So I can solve for A or B. Which one should I solve for?
A.
Why?
It's just like that.
Well, I can't quite solve for A yet because I got A and B. So as I just said, A or B should apply to any value of S that I plug in. What if I plug in S equals minus 2 and evaluate this equation at S equals minus 2? Then what I'm left with is 3 times minus 2 plus 7 over minus 2 plus 3 is going to be equal to A plus B times minus 2 plus 2 over minus 2 plus 3, right? Yes? So this here, this B, I don't have to do any work on the denominator. The numerator tells me that this goes to 0. So this term evaluates to 0. And what I'm left with is A equals 7 minus 6 over 1 equals 1.
Please plug that into this.
Well, I still need to solve for B. And there's a bunch of different ways to do it. What I like is consistency. I like to do the same thing over and over and over and over again. Why? Because I get good, right? It's the whole thing about 10,000 hours. You do the same thing for 10,000 hours, you get to become an expert at it. Right? Well, that's the rule of thumb. If you spend about 10,000 hours, you become an expert. That's why you practice, like tennis players practice for hours and hours and hours. And as long as they have the physical ability to do it, like, you know, they're not slow or have a bad leg, then they get to be really good. Most people can't do 10,000 hours doing the same minutia stuff, right? They get bored. I go into the gym, well, I used to until I got hurt, but I do the same minutia thing for hours and hours and hours, but I like it. But I don't actually do the same thing because I wouldn't stick around. So anyway, let's do B. So let's multiply by whatever's under B. So 3s plus 7 over s plus 2 times s plus 3. Multiply by s plus 3 equals a times s plus 3 over s plus 2 plus b times s plus 3 over s plus 3. Am I going too fast? So let's cancel out what we can. Goodbye, 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 and rewrite 3s plus 7 over s plus 2 equals a times s plus 3 over s plus 2 plus b. Evaluate both sides at s equals minus 3. And what do I have? 3 times minus 3 plus 7 over minus 3 plus 2 equals a times 0. I don't care what's in the denominator as long as it's not 0, right? As long as what's in the denominator, I don't care if it's a complex number or not, as long as it's not 0. Because then I have a 0 divided by 0 thing, and then I have to start doing limits and all that stuff. So we don't want to do that. Is 2. So my final equation equals 1 over s plus 2 plus 2 over s plus 3. That's the partially expanded form.
So if there are 7 roots, you'd have to do that at 7 times.
Yes.
Can you create a MATLAB code to get the A and B probably?
You could do MATLAB code to do that, or MATLAB code actually will do partial fraction expansion for you. There's an actual function that does that for you. Any questions on that? Am I right?
Yep.
How do you know? Plug it in? I did already, right? Why not put them back under the same denominator, see if we get the same results? We should end up with 3s plus 7. So s plus 3 plus 2s plus 4 all over s squared plus 5s plus 6. What?
You just do things really fast.
Yeah, I'm sorry.
You just multiplied s plus 3 times 1 and s plus 2 times 2. And then
Okay.
just adding them together.
That was fast?
Yeah, you do it.
Yeah.
It's like you're making a numbers and putting on.
I didn't. Didn't I just put these under a common denominator?
I know what you did now. You just did it so fast. I
Oh.
couldn't figure out what you did.
I thought that's what I said. We'll put it under a common denominator.
Yeah,
But if I go too fast, just slow me down. That's okay. So let's check. I have is that the same as that?
yeah.
So this is okay. It works. It is good to go. So now I can take this back. I guess I can erase this section of the board. I can take this back into the time domain. And to do the inverse Laplace transform, you do not have to do any calculus. All you got to do is go to your book. There's a table. I think it's table 5.1. I didn't bring the book with me. All you need to do is make your functions look like the table. Okay? So in the table, you'll have f of t and f of s. The f of t will have 1 over, e to the minus alpha t corresponds to 1 over s plus alpha. That's in the table. You can look it up. Not in the table?
Not 5-1.
Let me look at the table. I thought it was 5-1. Maybe it's 5-5.
So lost, I'm following you, but that's not the table.
That's not the table, yeah. That's a figure. That's the table. Everybody see that? That's right out of the table. It is table 5-1. You just go to the table and you see f of t and f of s. So this has s plus 2 in it, right? Or s plus 2? That's s plus alpha. So 1 over s plus 2 is e to the minus 2t. And 2 over s plus 3 does not look like the table. But 2 times 1 over s plus 3 does. So 1 over s plus 3 is e to the minus 3t. What do we do with the 2? Why can we times it? Go back to the first class. What did we say about multiplying a constant in the time domain? What is that equivalent to? Multiplying by that same constant the Laplace transform function. So k times f of s is the same thing as doing k times f of t in the time domain. So this is just 2. So my f of t for this is 2 e to the minus 3t plus e to the minus 2t. I will pause because for those of you who haven't seen partial fraction expansion, it can be a little intimidating. But you will be doing, I don't want to overstate this, but you will be doing partial fraction expansion a lot. You'll be very good at it at the end of the semester. And one of the things that I want to say is that it's not intimidating. You just need practice. It's just algebra, right? There's no fancy dancy calculus here. All we've done is algebra, isn't it? Or haven't we? You want to do a little practice? Do an easy one before we do one with complex roots? Do you want to do a third order? Second order?
Second order.
All right. Can I erase my board? That's the end. That's it. You've done all your work. You wrote it. So you wrote a differential equation, right? So that's the thing. We have a differential equation that has a bunch of derivatives and integrals in it. We take that to the Laplace domain by multiplying or dividing by s to come up with an f of s function. Then we solve for our f of s function and do partial fraction expansion, right? Then we take that back into the time domain. So you can have an equation 2f prime of t plus 3 integral of f of t plus 4 f double prime of t equals some input y of t. I can take that equation just by multiplying or dividing by s in the Laplace domain, figure out what f needs to be, right? Because then it's just a bunch of multiplying by s's or dividing by s's. Then do partial fraction expansion. Then bring that back in the time domain. And when I come back from the time domain, I know what f of t is. Whereas before, in your differential equations class, what did you have to do? All this waving your hands around to come up with a that meets that criteria, right? So if you have a homogeneous equation, that's equal to 0. You solve for f of t, right? Did they say homogeneous or homogeneous? I don't know. Homogeneous? Okay. I think it's homogeneous, but some people say homogeneous.
I've heard it was homogeneous.
You say homogeneous.
I just say it's set equal to 0. I didn't even know why it matters that it's equal to 0, that they call it homogeneous. I just happy. All right, so let's do another one. Let's see, let's just go with 3. That's your f of s. Find f of t. 5 minutes.
That's 5, right?
It's 3 over s squared plus 6s plus 8. Do you want me to leave any of the board stuff up? Would that be helpful, or?
Yeah, leave that up.
Okay. Couple more minutes. Yes, sir. Oh, I don't know. I just dreamed this one up. You'll know when I know. All right, any answers?
Couldn't answer the quadratic equation.
All right. Would you like more time, or do you want us to go through it? Who wants more time?
I don't.
Who wants to go through it?
Well, I'd like more time to do 3 over 2.
Well, that's what I'm saying, because we have class time is precious. Who would like to go through this now, loud and proud?
Yeah,
I
no.
want
All
to see if I can get that one.
All right, you're ahead of me, so you'll beat me. How's that? So quadratic equation. Right?
Yep.
Square root of 4.
Negative 2. So this becomes A over S plus 2 plus B over S plus 4.
So, I guess in the first, like, when you showed us 2 different ways to do it.
Now, I actually only showed you one way.
Okay, all right, so I just got the first part then.
Okay? So we got to get A and B. So let's solve for A. If you feel comfortable, A is going to be equal to 3.
Well, wait, actually, sorry. You showed us you could defoil it, and,
I didn't defoil it.
well, I'm just saying,
You could.
you could. So did you show us 2 ways to get the equation? It was,
To get the roots?
yeah, the
No.
So,
He just did the question.
I just did the quadratic equation.
well, the first thing I did was defoil and got S plus 2, S plus 4.
I don't know defoiling. I've never heard that.
So it's like, you just look at that trinomial or whatever it is.
You have S squared plus 6, S
Quadratic
plus 8.
equation.
So you can just break it down. So you know.
But how do you know what the values are?
You
It's like
kind of
what-
just use your.
Just figure it out.
What
What multiplies?
It could be 3 plus 3 is 6, but then,
So you have some intuition, essentially, to how to get there, right?
yeah,
What 2 numbers multiply to 8 by adding 6?
yeah. It couldn't be 3 and 3.
Okay, so you have intelligence to do it. What I'm saying is a quadratic equation, it's just automatic. You don't even have to. You can do that way if you want.
You can't do it,
You have to use
quadratic, but for this one.
And you will be using quadratic very soon because you can have complex roots.
All right, cool, just wanted to be clear on that.
Yep.
I wasn't sure what the difference was. What we do.
All right, so can I do this? A is going to be equal to 3 over S plus 4, evaluated at S equals minus 2.
You're just skipping all the other steps.
Do I need to write all those steps how I got there?
B's going to go 0.
Anybody? Do I need to write the steps? Loud and proud. You need me to write the steps?
Oh, no.
Okay. So A is equal to is 3 over 2, right? It's 3 halves. And B is going to be equal to 3 over S plus 2, evaluated at S equals minus 4, equals negative 3 halves, right? Yes, sir.
So like with me, when I pulled it out, like I had A over S plus 4. B over
Doesn't matter. It's the same thing. And I'll tell you why. Because now we have equals 3 halves over S plus 2 minus 3 halves over S plus 4. I'm ready to go to the Laplace domain looking at my table. My f of t now is equal to 3 halves e to the minus 2t minus 3 halves e to the minus 4t. You and I should get the same, you guys should get the same results. That's what I'm saying. It doesn't matter if you pick A or B. It's all that matters is your f of t equation.
A and B usually end up being equal.
No. Matter of fact, they very rarely do. Okay. Ready to do one with some complex roots?
Hey, Paul,
Yes.
question. When you, oh, never mind. Nope, I'm all set.
Okay. Let's do a complex root. Okay, so the next one we're going to do is
S to the seventh or second?
5s over plus 40 over s squared. We're not going to work with s to the sevenths because to factor that out is a real pain. So let's do quadratic equation. I'm sorry? 24. Where's it's 29.
Yes, this one definitely.
So this is equal to -4 plus or minus the square root of -100 over 2, which is equal to -4 plus or minus the square root of 10j over 2, which is -2 plus or minus 5j, right? Complex roots.
I'm gonna ask, you just do that in your head? You ever heard
Do what in my head?
Well, you just divided, you just -4 divided by 2, then 10j divided by 2.
Yeah, which part?
Nothing.
Okay.
What, so it's 10J, because it was a negative 100, right?
Yeah, because it's a.
-100, so you factor out the -1, right? The square root of -1 is what? If you don't like what I did here, maybe I did this too quickly, that's equal to the square root of -1 times the square root of 100, right? This is j, and this is 10. Okay? So if you look at the table has one that kind of looks like this, because what you would end up having in the denominator is you have s plus 2 plus 5j plus s plus 2 minus 5j. That's what the denominator looks like. These are complex numbers. You'd like to get rid of them. So what's easier to do is to say s plus 2 quantity squared plus 5 squared. So all I did is I took the s plus 2 and I squared it, and then I took the 5s and I multiplied them together, and I ended up with the 5 squared. Because when I multiply the plus and minus 5j's through there, they'll cancel each other out. Do you buy that?
Where's the S from?
Where's the s from? That's the root. That's what you evaluate at. You evaluate at -2 plus or minus 5j. That's what s is equal to.
Okay.
So would it be -2 on those?
No, because the root is what you plug in. You plug in a -2 plus or minus 5j, so that's why I have that there. Okay, so that kind of looks like the table, but not exactly. If you look at the table, it's you have items 5 and 6. It has to have something that looks like this. It has to be s plus alpha squared plus omega squared plus that's what the table looks like. You have one with an s plus alpha and one with an omega in the top terms. So all we need to do now is make this numerator. So we have 5s plus 40 has to be over s plus 2 squared plus 5 squared.
Where's the plus 5 squared come from?
When you multiply these two, put them on a common denominator, you're going to end up with -5j times +5j. What's that equal to?
Was it not far?
Pardon?
Was it 25?
Yeah, is it 25?
+25. What's 5 times 5 equal to?
25.
What's 5 times 5? 5 squared. Same number. So this is what we have. We have the 5s plus 40. We want it to look like that, right? So the first thing we know is we need that to look like s plus 2 squared plus 5 squared. So we know what alpha needs to be. Needs to be equal to 2, right? So for the first one, we need to have an s plus 2 up there, don't we? To make that work. I have a 5s plus 40 up here, don't I? So my numerator is actually 5 times s plus 8, right? So if I put the 5 out front here, right? I've got s plus 2 times 5, don't I? Right? What am I missing? 30. Right? But does this look like this? Not quite. So that's going to be equal to 5 times s plus 2 over s plus 2 squared plus 5 squared. This one's good to go. Now I need it to look like omega over s plus alpha squared plus omega squared. So I have s plus alpha squared plus omega squared. I need a 5 up here. I've got 30. How do I convert 5 into 30? Factor out of 6.
How do you, the omega look like a yield, so I was going to confuse any formula writing.
It's omega. So going back into the time domain, f of t is equal to 5 e to the minus 2t cosine of 5t plus 6 e to the minus 2t sine of 5t.
So is this like using the A and B, just your A is the S plus alpha and your B?
No, this is not using a and b at all.
Can you go over it real quick?
This is just factoring it out.
Just putting that back into the final FT.
So I look at my table, right? My table has s plus alpha over s plus alpha squared plus omega squared, right? That's in the table. I think it's T5. Does that look the same?
Yep.
Yes. So I just put my 5 and multiply it by the equivalence in the Laplace. So this is f of s. My f of t is e to the minus alpha t cosine of omega t. And for my next one, e to the minus alpha t sine I have omega in the numerator.
Which is what we have to prove today, the cosine one.
Which is what you proved, except you didn't have e to the minus alpha t. Questions? Easy? Hard? This one is really not doing any the partial fraction expansion you're doing is not doing that a plus b stuff. This is just, we need to make the table. So we knew what the denominator looked like. We don't have to, the only time you do partial fraction expansion is when you can't get the denominator to look at the table. There's another function that's in here. That's when you need to do it. But in this case, we only had the one element, so we don't have to do partial fraction expansion on that. Okay? Another one? No? Your head hurts? Why? What's going on? Oh, am I going too fast today?
Yeah.
How can I help you learn this stuff? It's just grinding it out.
Yeah, I'm following everything, it's just, it's a lot.
It makes sense.
We got 5
Does
minutes.
anybody feel overwhelmed? You can be honest. Pardon? I- Pardon?
This isn't the stuff.
This is not too bad?
No, because they just calculate.
How about we start on one and you can finish it over the weekend? So we definitely have to do partial fraction expansion.
I'm
Oh,
sorry, hold on, those 5 are,
Yeah.
I have the hardest.
Fives are probably not.
fives.
Which
5 was
Maybe we switch to
S plus 5, S squared plus 4S plus 5.
S plus
S plus 5.
S plus 3, yeah.
S plus 3.
Okay.
I mean, you wouldn't put 5 plus 3 S's.
You don't need to because it's in my notes, right? Except for this one's not, though.
I'm just saying.
Yeah,
You
you would,
think
why would you
you
put
have
5
five
plus
plus
3?
no idea.
Yeah, you wouldn't put 5 plus 3, you would put 8. So
I wasn't going to be that obvious, but
yeah. What is that? S squared plus has to be
4S plus 5. So the first thing we need to do is quadratic equation.
Yeah.
So that one was EBS minus 1S
Defoiling it? That's not what I got. You can't get S minus 1 times S plus 4 because S minus 1 times S plus 4,
S plus 5.
S plus 5. So would you get a positive 5 here when you foiled it out?
Yeah, no, you can't.
You have to.
Can you see why defoiling has been defeated?
It doesn't work all the time.
It doesn't work. Yeah, when you start getting complex roots, it doesn't work. Come on, I'm pretty quick on my toes. Defoiled been defeated. Nobody laughed.
That's pretty good. That was good.
Peter, you're right. Everybody's gonna have to take a nap.
That seems like a dad joke.
It's not a dad joke. It's a math joke. So, the way that I would start this one, plus b over s plus 2 plus j
Why is there a C?
I've got 3 parts.
So,
Because you can't go back, you can't do what we did there with that s term in the numerator. So when you do partial fraction expansion, you gotta be very careful about adding s's when you don't expect it to. You would actually have a b, s, c and combine them together, but we're gonna just do this the root way, and then I'm gonna show you a sneaky shortcut trick way to do that.
so we have to use partial fraction here, but not here. So,
You don't have to do it here because this one is multiplying another function, right? Where the other one only had s squared plus 4s plus 5, or 20.
This one only has the one that we did before.
The one we did here?
No, not that one. Before that one. Only have one thing in the
I do have one.
denominator, so we had these.
You had to do that because you had 2 separate functions, s plus 1 times s plus 2, right? Or s plus 2 times s plus 3. Those are 2 separate f of s.
Okay.
Over here, we have 3.
I have a quick question. Though.
Yes.
Why is it S plus 2 plus J and then the other one's just S plus 2?
No, this is minus j.
Minus J.
Have a great weekend. Told you I'd let you out early, right?